First of all, thank you. Hi, everybody. My name is Riku Eronen, and I work as a software director at Mapvision. And it's my pleasure today to tell you about using machine vision to ignite a paradigm change in automotive industry. So I will first start with describing the industry a little. Then I tell a little bit about Mapvision and the need for our product, something about our technology, and at the end, I will end with a quite practical use case of our product. So this is a car, as we see it from the driver's perspective. Of course, there is lots more than we see here in a car. In fact, it is one of the most complex devices that we use in our everyday life. In fact, here are the keys for my car. Hands up, how many of you have seen my car? How about how many of you would be able to drive it if I gave you the keys? Yeah, something like I expected. So there are thousands of technical details to make car work, but still the user interface is so easy to use that all the technical breakthroughs are made accessible to all of us. So this is what it takes to build cars. This is a modern car factory in Germany. BMW produces around 360,000 cars per year in this factory. That is around 1,600 cars per day. So we're talking about big scale. About Mapvision. Mapvision provides digital 100% inline inspection to car, body, and chassis components. That is cross-car beams, subframes, rear axles, body modules. Basically, anything that is put together by welding and is ending up to a car. So, for decades, automotive quality has been controlled using gauges and coordinate measuring machines. A gauge on the left there is a device where you put your part in and you try to push those pins through few holes. And if all the pins go through, the part is okay. On the other hand, coordinate measuring machine there, it is able to measure 3D positions of features really accurately. But it takes lots of time to go through all the features that should be measured. As quality standards have risen, an intermediate technological step has been introduced. And the step is robotic measuring systems. A robotic measuring system is basically optical or laser sensor or both attached to a robotic arm. And it has both reaching and accuracy limitations of a robotic arm. And fortunate for us, Mapvision has a software solution where there is no moving mechanical parts and which is able to measure all needed features within the production cycle. Same kind of paradigm shifts have been seen in many technical fields already. I think most known one is music distribution and iTunes. So previously, mechanical things are now done purely with software. So what does it take to be able to make such a paradigm shift? First of all, you need to have a need for the change. So something that is not done optimally, it's slow, too slow, not good enough, or something. It depends on the subject. And after having need, you should have an enabling technology that is mature enough to actually be used in practice. And if you have all of those, then you are left with the hardest one, which is human acceptance. I will now go through these components of this paradigm shift that Mapvision is igniting and facing. So we will start with the need. The need for inspecting comes from the production challenges. So car manufacturers are facing an increasing complexity of variants, as well as amount of the variants in the production. This is due to the fact that cars are built to the order nowadays, so the owner can select his equipment from high variety of the equipment, making the cars unique and different from each other. At the same time, there is really high pressure on building lighter cars and designing lighter cars and using lighter materials increase the quality requirements again, as the production tolerances are smaller. And of course, cost is always critical, especially when margins are low and competition within the industry is high. What these things do, they actually force the automotive industry to deliver 100% quality, meaning that no bad parts should be delivered, or better yet, produced. But with processes that are by nature unstable, this is, with one word, hard. Before Mapvision, the quality was controlled using coordinate measuring machines and robotic measuring systems, which all involve mechanics. And the mechanical nature of those machines actually make them do compromise between accuracy and speed. So that makes them not able to measure all parts, which ends the manufacturer to actually do a sampling inspection. In sampling inspection, individual random samples are taken from the process, the red ones there. And only those are then inspected. The sampling rate is at best 1 inspection per 100 produced parts, but it can be even so low that only 1 part per 1,000 parts is inspected. And as you can see, there is there's no real way of saying what's going on in the process, which then results to the fact that there is no final control over the process, and the process cannot be adjusted. So I think we all can agree that there is a solid need for inspecting all the parts. We can move to the technology and see how it's done. Mapvision utilizes three major technologies in the measurement. Machine vision, to find the interesting features from the images. Photogrammetry, to calculate 3D positions for those features. And 3D CAD, to first teach the measurement for the measuring system, and then at the end to visualize the results with human understandable way. Here you can see our teaching software. It's called Toolbox. It's used for designing the measuring system, and it is used for changing the parameters on the measurement. But most importantly, it's used for teaching the measurement, so what should be measured. Here we have two features that are selected to be measured. The blue balls in the middle, they are the nominal positions for those features, so where the feature should be. And the blue edge, it is the edge that makes the feature and is used for measuring it. After teaching the measurement, the measuring system takes images of the part. We use multiple cameras, take pictures from the part from different views of angle. And for those images, we use the machine vision. Here you can see a correlation surface, and the line there is algorithm's path to the minimum. So the minimum being the place of the feature in the image. So machine vision tells us two things. First of all, is the feature produced as planned? So basically, is it there or not? And if it is there, it tells us where it is in the image. Having all these 2D positions for the features, we then use photogrammetric functions to calculate the 3D position for the image, for the feature. So here we can see images, and the dots there are the positions in 2D, and then we use functions to actually find the 3D position there. That's like in human words what we do. That position then is at the end compared to a nominal value, and that comparison is used to detect whether the part was good or not. So would it fit to the place where it should fit? That's about the measurement and the end of the technology part. Now we are left with the human acceptance, and I would really like to start it with talking about money. As money, how boring it might be, is one of the major things that makes people buy into the new things. Here we can see a graph that shows a cost of a quality problem in production chain. it starts from tens or hundreds of euros per part on the component production phase. So being material expenses and that kind of stuff. And if the faulty parts are caught right after they are produced. Already in core assembly phase, we are talking about significant thousands of euros per part. Depending on the part, might be even tens of thousands. Meaning that if we have, for example, subframe that doesn't fit to the car, the line has to be stopped and the car taken off there. But the cost ends up to hundreds of thousands or even millions of euros total if cars with faulty parts are actually delivered to end users, being customers, drivers. Because those cars usually need to be recalled and checked manually. Do they have the fault or not? Because we don't know. It's quite obvious that anything that can shorten the feedback loop will decrease the costs dramatically. But would it be even better if you would not produce any bad parts to begin with? And that's where having all the results actually starts to pay off. Let's imagine for a moment that we are in charge of a production line. There is a problem and we are about to adjust the line. This is what you would like to use. This is our process adjustment tool. It's designed for analyzing the need for the adjustment and as well as confirming the made adjustments. Here I have pre-selected you a product, interesting time frame, loaded the results, selected a feature, and by selecting only the first half of the parts, we get to analyze the need for the adjustment. Here we have a 3D view with part CAD model and error vectors. Error vector is a vector that points from the nominal position to the measured position of the feature. So it tells us the direction of the difference and the amount of the difference multiplied by a constant. So if we plan that my hand should be here and it is actually here, the error vector is that, and for visualization purposes we actually multiply it to make it visible. But it is also color-coded, and each one of those red ones there is a bad part. So we have a problem. But looking up to the graphs, we can see that the feature is actually produced around 1.6 millimeters down from the nominal on the x-axis. And that's the adjustment that we should do. Now, being in charge and being bold, we go to the production line, push button, okay, stop the line, open door, go inside the security fence, go to the welding cell, open some bolts, make an adjustment, come back, close the door, start the production. Then we wait for 5 minutes so that we get some data back. Now I've selected the 5 minutes after the adjustment, and having these 10 parts, oh no, it's quite obvious that there has been an error. Maybe we made a mistake there. Humans tend to do that. machines might break or whatever. But no worries. We can go back and do a corrective adjustment for that. So we go back, open the door, make an adjustment, close the door, start production, and wait for the parts to go on. Now that we have selected the last parts, we can confirm that the graphs show the feature almost exactly on the nominal line, or at least really, really close. And also, all of the error vectors there, they are short in green. That's okay. That's a good thing. Now just imagine doing this with a coordinate measuring machine. It would mean that you have only one result per every 100 produced parts. So having an 30-second production cycle and needing 10 parts means that we would wait almost 8 hours to get the 10 results to actually realize that we made a mistake. And in the meanwhile, we would have produced 1,000 parts without knowing, did we improve the process or did we break something? I don't know about you guys, but I wouldn't do any adjustment on that, no. Not me, too risky. And that's kind of one of the key things that makes it hard for new technologies. It's basic change resistance. We are used to doing things in a certain way. We feel safe there. And things that are safe there, or better yet, things that are actually harmful there might be really useful in the new technology, but we are too scared to try. As we all are human beings, and human beings usually don't believe until they see with their own eyes, I would like to revisit the thought of making the technical breakthroughs available for all. Here we have an animation. It actually has 2 frames only. One with the good part and other one with the bad part. Maybe we do a hands up again. How many of you would be able to say what's wrong with the other one? Or how many of you would like to have that one in your car? Thank you.
Thank you, Riku. And now we also would like to introduce Lasse, who is a colleague of Riku, for a Q&A. Do we have any questions from the audience?
Right. So usually when you want to get the 3D coordinates for a point, and you do it by taking multiple photos from different angles, you need to know where, what 2D coordinates this point is in multiple photos Because if there's ambiguity there, like there is with different lighting, and if you don't know the exact shape of the thing, and for example, if you take a photo of a flat surface that is of same color, you cannot just use image recognition to recognize a specific point at different photos. But if you have for example, marked pencil point there, then you can accurately say where it is. So it depends on the images of if this is kind of a problem, or if you can do accurately this 3D point location. So do you have this kind of issue in your images, or do you use something like, for example, a laser pointer to detect the position of a point in different images so that it's the same point?
That's good point. Most of the features that we measure are actually some kind of edges, but for surface points we use structured light. So we project a light on the surface and measure that. So kind of laser thing, but not with the lasers. Yeah.
Are there more questions?
Hi, thanks for your presentation. About the 3 challenges, you mentioned that the human acceptance was maybe the most difficult one. So what's your key secret to tackling that?
Work, convincing, providing good value. It's usually, at least salesmen say that they can always sell one machine, but the customer needs to be made happy with that one, so that they buy another one. At least in the industry that we are working on, there are like really big players, and it's not enough to sell one machine for one customer. So doing your homework, understanding the customer, and delivering value to the problems that they actually have. So wouldn't want to come up with the problems that they don't have. There needs to be the understanding of the problem of the customer.
All right, thanks.
Hello. Thanks
Hello.
thanks for your info.
Thanks.
About what is the accuracy of your measurements? How accurate measurements can you make from the parts?
Yeah, I believe Lasse can answer
Yeah.
this one.
We've just been thinking about what it would be officially. Now, what we give out is not a laboratory value. That's something you need to keep in mind. If you look at the accuracy of a coordinate measuring machine, the reference is generally to a laboratory part, a prismatic part, very sharp. Now, we have to use actual production parts to define the accuracy. And we're talking of basically accuracy comes from correlation and repeatability. Repeatability with the production parts is about 0.02 millimeter, and generally correlation we achieve with the coordinate measuring machine is around 0.15. And that means that our technology basically works with this size of parts, is able to supervise the tolerances that are typical for welded parts, and they are like typically 0.3 to 1.5 millimeters plus minus. And that's where we are. So with this size of a unit, we are not able to measure engine parts, but our accuracy falls very well in the category that is common for welding and cast structural parts. And in fact, once we have started looking at it, basically our real performance with actual production parts is very close to a coordinate measuring machine. The difference is that the coordinate measuring machines measures about half an hour what we do in 30 seconds. And secondly, coordinate measuring machine delivers a result. But because we have many cameras, we have actually internal correlation within the system, so we can tell that the number was okay, and the guys can do, as Riku is showing, you can go straight and adjust the process with the inline data. This is not possible with any other technology.
Yeah. So basically having all the results, we get an average over those, and that tells quite accurately where the process is. So
Are there any more questions?
Thank you. Question about this, like on your example, you were stopping the production line, adjusting and so
Yeah.
on. Is it going that way, that it's sort of closed loop, that the measuring data from your system is then fed back to the manufacturing machines?
yeah.
So you don't need to stop the line, it adjusting itself within, as long as it stays within the threshold or something.
Yeah. That's kind of where we would like to be. Traditionally, the welding jigs that are used to have the components in are manually adjustable. So there are really few of those that are digitally adjustable. But as soon as those are like used, we can create a closed loop and actually do some kind of automatic analysis of the process and adjust the process using the results automatically. But until then, for most of our customers, it means that the line has to be stopped for adjustments, or the adjustments are made during like normal daily maintenance stops.
This actually, it's maybe 2 points from commercial side. We can say that our system is completely Industry 4.0 compatible, so that would be on our behalf doable today. But the welding jigs or the processes are not adjustable. But that again comes to the logic of mass production. It would need to pay off. So automatic adjustment doesn't pay off in mass production, which runs, you have a line, you set it up, it runs for 6 years. In the beginning you have a lot of adjustment, and that the users haven't seen it necessary to put any automatic flexibility in there. That is a possibility that basically, from our point of view, would open up new markets, but our home market is through mass production, and it doesn't pay off today. It might do it, but in fact it is an argument for our selling. We are Industry 4.0 compatible or Smart Factory compatible today. This data can be used for automatic adjustment. And the breaks, it's not process industry. They make break for lunch and for coffee breaks, so you have breaks every 2-3 hours. So getting the break for adjustment is never an issue.
Interesting stuff. Reliability engineering wise, I think those clients are still using those automated coordinate measuring machines, whatever they were called,
Yeah.
even if they are using your systems.
Yeah, there usually is the measurement laboratory still, and from our point of view, it's good that there is this check for the check, so we can confirm that our machine actually works using the other one.
It would be possible to follow the production only optically, but correlation with another machine is always good if you look at measurement basically. So what we do is still the standard is the coordinate measuring machine, and we deliver CMM compatible results, and therefore when the system is set up, it is actually adjusted against CMM results. So once that's done, it runs independently, but basically in the beginning we have like native accuracy, and we get offsets for results to make them compatible with the CMM. So that's true. It still refers to CMM, and we'll be doing that for a while.
Are there any other questions? If not, thank you Lasse, and thank you Riku for this very interesting talk, and I wish you good luck.
Yeah, thank you.